Thank you for joining us for today's SCL Interdisciplinary Research Center seminar. This is our second seminar in the academic year. Today, we are very excited to have with us Dr. Koki Ho. Professor Ho is an associate professor in the School of Aerospace Engineering at Georgia Tech. He's also the director of the Space Systems Optimization Group at Georgia Tech. Today, he's going to be talking to us about the logistics of space exploration. It's a very exciting topic. Logistics in general is very exciting. In this area, I'm very excited to hear him speak about this. There's a lot of things going on in this field, as I'm sure you've read and heard about the Artemis launch this week. So there's just a lot going on, and it's great timing for Koki here to talk to us about that. So we're looking forward to your presentation. Thank you very much for your time, and I'll let you take it from there.
Yeah, thank you very much for the introduction. Hello, everyone. So my name is, again, Koki Ho. I'm a faculty in Aerospace Engineering, and here I think this is the first time I'm giving a talk in front of the audience who are not in Aerospace Engineering. And I recognize some faces here, including my own students. Thank you very much for coming. And so for those of you who have heard my talk in the past in Aerospace Engineering, probably some of the materials and maybe a lot of materials you have heard of in the past. But for those of you who have not, or those of you who are in a different field, I hope this talk can be an exciting starting point for our discussion and maybe even potential collaboration in the future. Now, just a little bit about my own myself. I am originally I did my undergrad and master in Japan at the University of Tokyo. I was in aerospace engineering field major, and I was working on a small satellite design for especially the Star Tracker, which is an attitude control sensor, attitude estimation sensor for small satellites. So that was kind of my original background. That's how I started to get into the research field. And then I came to the US for PhD, and at the time I thought I wanted to do something different. I wanted to maybe look at a little bit bigger picture than what I was doing previously. And that's how I started to get into the system level optimization and system level design for space exploration missions. And so that's what I have been working on since then. And this is exactly the topic that I'm going to talk about today. Before I get into the technical topic, I just want to briefly introduce my group. Again, some of the students are here, but so I originally started my faculty career at the University of Illinois, Urbana-Champaign. So I was in 2016, and I moved here in 2019. And currently we have about 10 to 15 grad students and some other undergrads working with us. And the members, alumni from our groups have, some of them have chosen academic path. We have 3 plus university professors. The reason I added plus because there's another one, the 4th one, who was not technically my student. I was not his thesis supervisor, but he was a research assistant in our group. So he's now a professor at Princeton. And then we have more than 10 in industry. Our work has been sponsored by these sponsors since 2016. So over the past 6 years, we have been as a PI or co-I on a variety of different research projects worth more than $10 million, and out of which about $3 million has been dedicated to our group itself. So that is kind of the rough scale and what we've been, how it looks like, our group looks like, and this is what we do. So the mission of our group is to create optimization methods and the models that can be used to tackle the growing complexity in space mission design field. Particularly, we're trying to look at the intersection between the more traditional logistics optimization, modeling, and the space systems. And we're trying to pioneer this logistics-driven modeling and optimization in space mission design. So these are just 3 applications we have looked at. The first one, which is the one that I will spend the majority of my talk today, is about space exploration mission design at the campaign level. So campaign here, we define it as a series of coordinated missions. So it's a series of missions, and these missions are operated in a coordinated way. And instead of looking at mission design of each of these specific missions or its a trajectory design, which is a more traditional way to look at space mission design, we are looking at a whole campaign and see how we can design the campaign in an optimal way. So that's kind of the perspective we're trying to take. And that was also what I did during my PhD with my advisor, Olivier Devec at MIT. So he had Oli Devec with Dr. Simik Levy at MIT started the space logistics project, I think in early 2000s. And then after that, NASA kind of shifted their focus a little bit. So this topic has not been substantially funded by NASA, but we have started to looking at this problem from a new perspective, considering the new campaign that NASA has, including the Artemis program that is ongoing right now, and also the potential future exploration of Mars. So that's kind of the perspectives that I want to talk a little bit about in today's talk. And then, so I did my PhD in this area, and then after I finished my PhD, I started to also, of course, I continued research in this area, and I also started to look at other areas, which include the on-orbit servicing, assembly, manufacturing. So that is the idea of refueling or repairing satellites in orbit. So in the traditional paradigm, when satellites are launched, and if something goes wrong, that is it, and we have to launch a new one. We have to discard the existing one. We have to launch a new one because we didn't have a way to actually fix whatever malfunction that has happened in space. But there are new technology, especially the robotics technology, that have been developed to enable the on-orbit repair or on-orbit refueling and on-orbit servicing. So that can that has enabled a lot of new research area and new mission concept that involves the on-orbit life extension of satellites even after its fuel has been depleted, or assembling something big, right? Something some large structure that cannot be launched from the ground in one piece. Or manufacturing something, right? We have a 3D printing technology that has been demonstrated on International Space Station. Redwire, which is a company who did that, is also trying to do that in space, in vacuum space, so outside of the International Space Station as well. So if that is possible, we can maybe use 3D printing to manufacture something new in space. And why do we want to manufacture something in space? Because of course you can build something big that cannot be launched in one piece. Like I said, that's of course one of the reasons. And another reason is that you can, basically design you have a much larger degree of freedom for the design of the piece that you manufacture in space, because they don't need to, for example, satisfy the strict requirement during the launch phase and acoustics and all other, requirement that we have to go through if you want to launch something from the ground. So there are a lot of benefits in on-orbit manufacturing as well. So this is another area where the logistics will really come into play, because this is kind of what we're doing on the ground every day, right? We have this repair, we have this manufacturing, we have this assembly, in all other industry on the ground, but we're starting to have that in space as well. The last one here is a small sat constellation. So that's basically some new concepts that have been developed and implemented by SpaceX, Amazon, and OneWeb, and many other companies. And essentially, the idea is that to have hundreds or thousands of satellites in space, and to provide, for example, communication to the ground. And this is different from the traditional space systems in its scale, right? We're talking about a significantly larger number of satellites than the traditional satellite mission. So In the traditional satellite mission, we are talking about, a few satellites, right? At most tens of satellites. But here we're talking about thousands of satellites. So of course, there are a lot of different challenges coming from this scalability. And we'll talk about some of them later in this talk. So these are a few, applications we have looked at. Of course, we have also looked at other applications, but in today's talk, I will be mostly focusing on this first one, campaign level space exploration mission design. And then we'll talk about this second one, on-orbit servicing, assembly, manufacturing, and the small sat constellation a little bit towards the end of this talk. So the background, like why do we care about campaign level space logistics now? I kind of already talked about it a little bit, but this is a slide that have been used, I think from early 2000 in this space logistics context. So when we think about the past space exploration, especially human space exploration in this context, one of the representative programs is Apollo that sent human to the moon. And Apollo is a very complex mission, but if you look at the logistics, how it's treating its logistics, it's actually relatively simple. Basically, it carries everything you need to the destination and do its own thing and comes back. And that's the end of the mission. For the new mission, you launch everything again and do its own thing and comes back. So from logistics perspective, it's using a strategy called carry-along strategy. Now, International Space Station, which is have been operated for more than a decade now, it is kind of the other way around. It has its own station up there, and you resupply your commodities, you resupply your consumables, you replace your crew, and so on. So it's from logistics perspective, it's using a resupply strategy. Now, when you think about future space exploration, it's actually significantly more complex because we're considering multiple organizations involved in it, multiple launch sites, and then we're considering multiple destinations. Multiple destinations include Mars, which is our ultimate goal, and also the moon, which we plan to use to demonstrate a lot of capability that's needed for Mars exploration. And also everywhere in between, basically, right? We may send something to a Lagrangian point, which is a stable or unstable. It's kind of a equilibrium point in the cislunar space in the Earth-Moon systems. And we can take advantage of those equilibrium point to, for example, send some infrastructure there so that it can be used for communication, for fuel supply, and so on. And we can also have something in other orbit between Earth and the Moon. Gateway is a concept by NASA. It can be used as a staging point or resupply station for the Moon or Mars exploration in the future. So there will be a lot of numerous different destinations, unlike Apollo or ISS programs we have tackled in the past. So the pure carry along and resupply strategy would not work. So we need to think about the logistics to enable the effective and also robust space programs. And the space mission design is also complex, not only because of this combination of carry along and resupply, but also because of the technologies for in-space infrastructure design. So we have the emerging technologies to provide a fuel support in space. And fuel support, by the way, is very important because when you think about the rocket, more than 90% or maybe even 95% of the mass on the rocket is actually fuel, right? The rest, what you actually want to carry, the payload, is actually a very small fraction of what you're launching. So if you can get fuel from somewhere on the way, then that can save a lot of your launch mass, therefore also launch cost. And this fuel logistics infrastructure, there give two examples here. One is the ISRU. It's basically mining, right? Mining on the moon, for example. In this is a sketch, I think, by NASA, describing a potential concept for mining plant on the moon. And so this is like an oil field in space, right? So it's called in situ resource utilization, or ISRU. It can generate resource from the in situ environment, and resource here, I mean the propellant, water, or life support gas, and so on. And by the way, Georgia Tech is actually one of the big players in ISRU technology development. Professor Tom Orlando in I think Department of Physics, he is a PI of one of the big grants on developing the technology, or more on the science side, not necessarily on how we use it, but more on the technology development and science behind it. For ISRU and lunar science. So Georgia Tech is actually playing a very big role in ISRU technology development. So what's funny is that when I was a student, right after I graduated, I went to NASA headquarters to give a formal version of this kind of talk. And then at that time, like the reaction from the headquarters engineers were like, ISRU is like I mean, they know that of course the technology have been developed even within NASA, but it's more or less like science fiction because it's not happening immediately. But now it's part of the official NASA's technology roadmap. They have within Artemis program, they have ISRU is one of the key components that they're considering for their mission. So the technology advancement is really happening for ISRU. And propellant depot is essentially a gas station orbit. Is where you store this propellant. So after you generate some resource on ISRU, you want to store it somewhere in orbit, and so we need to think about where this gas station or propellant depot can be in the cislunar space, and it can be at Lagrangian point, which is again a set of equilibrium points in the Earth-Moon system. Or it can be in Earth orbit or lunar orbit and so on. So there are different options we can consider, and that's where the problem becomes logistics-wise, right? It becomes interesting from logistics perspective. Now, all these technologies are have their own pros and cons. So when you think about ISRU, if you're an ISRU engineer, you of course want to push for ISRU. So if you ask whether ISRU is useful or not, you may come up with a concept where ISRU will play a very important role and say, okay, let's see, you see in this example that ISRU can save mass by this much. But then if you're on the other side, right, you can of course come up with a concept where ISRU doesn't help at all, right? For example, you're just not stopping at the moon at all, right? You're just directly going to Mars. Then will ISRU actually help us or not? Not necessary. So it really depends on the mission design. It really depends on the concept. So when we think about whether ISRU is needed or not, or whether propellant depot is needed or not, we really need to think about this problem from the system perspective. So one of the questions we're trying to answer is, are these technologies effective and efficient at the campaign level? And if so, how do we deploy and utilize these technologies? So in response to this background, we have this research field called space logistics. ARAA is American Institute of Aeronautics and Astronautics. It's basically the organization that runs all the conferences and journals in the aerospace field. And ARAA has a lot of technical committees, and one of them is Space Logistics Technical Committee, which I'm currently chairing. So we define space logistics in this way. So space logistics is a theory and practice of driving space system design for operability and supportability, and of managing the flow of material, services, information needed throughout the space system lifecycle. So the key point here is that we're considering not only, we're considering the space engineering not only as hardware design problem, or not only as a trajectory design problem or control problem. Instead, we're looking at this as a commodity flow problem. We're looking at the flow of material. We're looking at the flow of services and information. And we're looking at the whole system lifecycle. We're not just looking at one particular trajectory that we're interested in, right? That's kind of the perspective, the unique perspective behind this space logistics compared with more traditional aerospace engineering. So this is a I think joke photo I found online. So it is having us FedEx flying in space. So this is essentially what we're trying to do. We're trying to introduce the concept of, that FedEx, Amazon, Coca-Cola, or those logistics company have been using. Can we get inspiration from those approaches and see how they will work in space? So from here, I want to give 2 examples in this area and discuss some of the technical contribution we have made in these 2 particular topics. And then after that, we'll talk about the on-orbit servicing and constellations topics as well. So the first one here, the motivation is to consider the space campaign and vehicle design altogether. So one of the unique challenges in space that is different from the terrestrial logistics is that we don't have a lot of. So I said that space missions are becoming more and more complex, but it's not as complex as terrestrial logistics, obviously. But instead, there's something different because we don't have many missions or many campaigns. We often design our spacecraft, with a campaign in mind, right? For example, SLS that was just launched earlier this week is designed with Artemis program and the follow-up Mars missions in mind. So we're not designing a generic spacecraft. We're designing some spacecraft for some particular program. That is very different from how, for example, we consider the logistics on the ground. We don't design a track, for example, for a particular network. So because of that, we need to consider the mission planning, which is essentially the mission sequencing, right? When we want to launch what from where to where. And of course, this also involves the trajectory design and so on. And the spacecraft design, right? Essentially the sizing of each module of the spacecraft, and maybe that can involve some of the component choices as well. And the infrastructure design, so how we design this ISRU plant. This is again another sketch and or program depot, right? So those are all coupled, right? Those need to be considered together. So the goal here is to optimize the space mission planning, in-space infrastructure, and vehicle design concurrently. So how do we consider a problem that can concurrently design all these elements together? So to enable that, the first step we take is to consider the space exploration as a network. So again, this is the concept that was originally developed by Oli Debak and David Simiclevi at MIT. And it basically considered this whole space. At that time, I think the network considered was not as complex as this one. Now this one, we are considering Mars and near Earth object and so on. So the network is getting more and more complex. So the idea is that we consider each of these nodes, each of these orbits as nodes, and we'll connect them using arcs. And each of these arcs corresponds to the trajectory, right? From one orbit to another orbit. So that is kind of the basic idea. And if we assume a chemical propulsion, which is typically used for space, for example, Mars exploration or lunar exploration, or for human, then a lot of this, trajectory calculation can be done separately. For example, you can find the optimal transfer from geotransfer orbit, the synchronous transfer orbit to, for example, low Earth orbit. So that means that you can find the time of flight and your fuel use to govern this transfer. And you can do the same for all arcs. So you can create a network, right? So that the space mission design is not about trajectory design problem anymore. I mean, the sub-problem, each of them is trajectory design. But at the system level, it is a network optimization problem. So one natural question is, how is space logistics different from terrestrial logistics? We already have a lot of techniques that we developed. I think one analogy that people often use is the airline traffic management, which is a significantly more complex problem in terms of number of nodes and arcs and compared with the space exploration map. Air traffic management, by the way, is also a part of the interdisciplinary field between aerospace engineering and industrial engineering, which is very exciting. And the space exploration is a little bit different. So different in multiple perspectives, sorry. The first perspective is the trajectory models. So in space, we need to consider different types of trajectories. So I said that in some cases we can pre-calculate the cost between one node and another node. That's true for some specific orbit and for under some specific assumptions. And for example, if you start to think about electric propulsion, which is another propulsion system that we often use, electric propulsion is different from chemical propulsion in the sense that it is a low thrust propulsion system, which means that you can only accelerate very slowly. So it becomes a control problem. You can't just fire your thruster and you're on the way. It doesn't work in that way. You have to continuously fire thruster over a long time. And because if you assume, for example, constant thrust, then depending on what mass you carry, your acceleration will be different. So depending on what you're carrying, right, your flight time will be different. So that is very different from, for example, airline, right? However many passengers you carry, mostly you arrive almost at the same time. But in space, depending on how many passengers or how much you're carrying, you may arrive at a completely different time. And you may take a completely different trajectory. And also in space, we can have time scale issues. We can have multiple time scales. For example, when we consider a trajectory from the Earth to low Earth orbit, it's on the order of hours to days at most. But if you're considering the orbit from the Earth to Mars, even if it's in the same network, it can take hundreds of days, right? So it's a very different time scale. So actually, the contribution of my PhD thesis was actually to consider these time steps in an efficient way. So we have, we'll see later on, but we can have a time expanded network, but we have a lot of time steps. So how do we choose the time steps? And we can have different ways to have an upper bound, lower bound, and so on. So after my PhD, I finished my PhD. I went to Informs conference to present that, and I met Professor Natasha Bolando, who was at ISYE. And actually, that is her field as well. She was of course not looking at space, but she was looking at terrestrial logistics, but she was also interested in time-space network, how to choose time steps, how to bound it, and so on. So we had a very exciting discussion, which is one of the reasons, by the way, I came to Georgia Tech, because of this excellent synergy between what we do and what Aerospace and ISYE does here at Georgia Tech. So, but these are some of the challenges, and the second one is the constraints. So in space, I just want to make sure that I have enough time. Yeah, so the constraints is also very different between space and the ground. So we have time windows. For example, when we want to, send some rocket from Earth to Mars using the most efficient transfer, then we only have a time window every 26 months. And we also have a launch capacity. Of course, we have similar, constraints for the terrestrial logistics as well, but they are enforced in a very different way. For example, time windows, sometimes you only have one shot, and that's governed by the stochasticity of the weather and other constraints. So the third one here I listed is the unique resource transformation mechanisms like ISRU. So it's like you're generating resource on the way. So that's not very common on the terrestrial logistics. When you have an airline, they don't necessarily, get new fuel, start generating new fuel on the way to, for example, Europe. The last one here, concurrent design vehicle infrastructure and network, which is what I talked about just before, because in many cases, we need to consider the vehicle customized for a particular campaign. So these are some of the unique challenges in space. So we have thought about how we can tackle these challenges. And one of the approach we have developed is time expanded generalized multi-commodity flow. It's essentially a multi-commodity flow, but it's a little bit more generalized. Generalized in the sense that it can consider the commodity gain and loss. and also commodity type conversion. So commodity gain and loss is critical in space, because in space, we don't pay money to go from one place to another place. Instead, we use fuel, right? We use propellant. So we lose propellant after a particular transfer from one node to another node. So the commodity gain and loss need to be considered. Again, like I said earlier, the fuel can be a large fraction of the vehicle. So you are losing actually a significant amount of mass if you want to go from one place to another place. And commodity type conversion. So when you think about human space exploration, and especially long-term human space exploration, human crew can consume food, and the food will it's not gone, right? It's the mass is still there, but it just convert its type into waste. And of course, you don't want to mix them up. You need to separate them when you consider the multi-commodity flow. And ISRU is kind of an example of both of them. It uses a propellant, of course. It generates propellant in a sense you're gaining mass, but it's also you can also interpret it as a commodity type conversion, because how much propellant you gain will depend on how much plant size you have brought and how much time has passed. And here is an example of time expanded network. You can consider different nodes, and for any node that has for example, commodity resource generation, consumption, then you can have a holdover that can capture this resource generation and consumption. For example, ISRU resource generation, or maintenance mass requirement depend on the time, and so on. And the optimization formulation itself is very similar as a multi-commodity network, except that again it is generalized. So we have this X, which is a vector that contains multiple types of commodities. And Y is a spacecraft. We consider the vehicle as a separate variables. And we split the flow into outflow from node I and inflow into node J. And this is in the time expanded network. So of course, the time stamp is also associated with them. This delta Tij is the time of flight from I to J. And the cost function can be anything, essentially what we're interested in. In many cases, we're interested in launch mass, because launch cost is a significant portion of the of what we do. But of course, it can also be a development cost and procurement costs and so on. And then we have a series of constraints. The first one is mass balance constraint. Essentially, it's saying inflow and outflow has to be balanced, and the difference has to be within the demand and supply at the node. And we have a flow transformation constraint, which is basically govern what's happening between this outflow from node I and inflow into node J. And that's where, for example, the propellant consumption can happen, ISRU resource generation can happen, and so on, right? And then we have this flow capacity, which is essentially saying that everything has to be stay within the capacity of the vehicle. And we have a flow non-negativity, which is saying that flow has to be non-negative, except when the window is closed. So when the window is closed, the flow is 0. And when window is open, the flow is non-negative. And the last one is a little bit tricky. So the last one is a spacecraft sizing module and sizing model. So we need to think about how we size the spacecraft and the infrastructure and so on. And we'll talk about this a little bit later on. And you may notice every other constraint except for the last one is linear. So this is the mixed integer linear programming except for the last one. And this last one, by the way, is not just one equation, of course. If you have a complex spacecraft design, this last one can be as complex as the rest of the problem formulation. This is just some several examples of this flow transformation and flow capacity constraints. For transformation, for example, when you think about propulsive burn, we have a convenient equation called a rocket equation that can tell you how much fuel or propellant you need to use to go from one place to another place. And that's typically described as a linear ratio, propellant mass fraction phi. And using that, we can write a constraint in a linear way, for example, like this. And flow capacity, for example, you have some capacity for propellant, capacity for payload. You can write it in this way. So this is just how you can define these constraints. So about the spacecraft and infrastructure modeling. So this is typically nonlinear. And of course, we can develop a linear model, and you can still run everything as a mixed integer linear programming. And we've done that. But the result can be very unrealistic. You can say, for example, very small piece of spacecraft, which is not really possible. So we need to consider nonlinear spacecraft. One way to model spacecraft is to consider spacecraft divided into three modules. One is three types of mass. One is the payload, one is structure, and one is propellant. Right. The payload is what you actually need to carry, and propellant is propellant, and structure is basically the engine or tank that is needed to support the propellant that you're carrying. So this is one of the model based on data. So we can have a series of existing spacecraft and try to fit it with some model, and this is one of the models. And of course, there are many other models existing out there. And for ISRU, we can, because we don't have a lot of data, we need to look at the model. And this is another, again, one of the models for ISRU. So ISRU is not just one big black box. It consists of a lot of subsystems, including the reactor, which is doing the chemical reactions that's needed to convert the resource that you get on the moon, the lunar soil, into, for example, oxygen or hydrogen. And we also have an excavator, right? That's kind of the rover that goes out and actually excavate and get resource, get soil. And we have a hopper system as well. And we have a storage system of the product that you have generated. And of course, in order for all of them to operate, you need a power system. So all of them are key components of ISRU, and all of them are coupled. Right? It's like an N-squared diagram, right? All of them are coupled with each other. And when we do the sizing, we need to consider all of them. So we can develop model for each of them. We did that in one of the NASA projects that looked into ISRU. And we consider this interaction between each of these subsystems, and we come up with integrated ISRU model. And these are just one example. We actually have developed higher fidelity models on this, but it's the simplest to show in a slide, so that's why I chose those. So the approach we took is to consider this network model like we discussed, and we consider this vehicle and infrastructure model as a piecewise linear approximation. So we can use piecewise model to fit, and it fits relatively nicely. It's of course not exact, it's not even optimal or feasible, but it's one way to model this, and it's very quick because everything becomes milk now, and you can get a solution as a result. And after that, we thought about a better way to handle that. So we consider augmented Lagrangian coordination approach to break down the whole problem. The whole problem is mixed integer nonlinear programming, but we can break it down because of the unique structure, mathematical structure of this formulation. We can break it down to mixed integer quadratic programming in a continuous nonlinear program. So we can use different solvers, nonlinear programming solver to solve nonlinear programming, and we can use Groovy to solve mixed integer quadratic programming, and we iterate, right? We can take the result using augmented Lagrangian coordination approach. We can iterate and eventually reach the solution we are interested in that is feasible and at least local optimal for the original mixed integer nonlinear programming. Now, of course, any nonlinear programming solvers will depend on the initial guess. So in this particular case, actually, this approximate solution using piecewise linear approximation is a perfect initial guess. It's very quick. It actually gives a near optimal solution. So we can first get this approximate solution and plug them into this decomposition-based optimization approach, and we can iterate and eventually reach the feasible and again, at least locally optimal solution, and hopefully globally optimal solution. So let's look at an example. So this is an example based on Apollo, not necessarily the replication of Apollo itself, but it is It's inspired by Apollo. So we have all these model parameters, and just for demonstration purpose, this network is super simple. This is just a series of parameters that we need to establish the model. And then we have this demand and supply. So this means that, for example, we have the crew and the equipment and the samples. We have an infinite supply for crew and equipment, infinite supply on the ground, and samples, infinite supply on the moon. So samples are basically the lunar rock that we want to bring back to the Earth. So we have infinite amount of lunar rock waiting on the moon. We have infinite number of crew and equipment waiting on the ground. And but we actually don't need infinitely many crew. We only need, in this case, 12 crew. And this 12 crew members, we have a demand of 12 crew members on the lunar surface at this particular date. And then after crew finish all the exploration at day 8, crew is ready to return. So we have a supply of crew return on the moon. And this crew will come back to the Earth. And on the ground, you have this demand. Right? And you have some equipment demand on the moon and the sample demand on the Earth. So that's kind of the problem setting we're considering. So if you run this optimization, this is one solution you'll get. So maybe one solution you'd intuitively think is to launch everything to the moon and come back. But the optimizer actually says a little bit different. It says that you can wait, you can have a part of the module waiting at low lunar orbit. The rest go to the moon. And then on the way back, you pick up some stuff from this low lunar module and comes back. This is kind of, so I said it's not intuitive. Actually, it's not very surprising result either, because it's much easier, it's much cheaper to leave something in between if you don't need this at the lunar surface. Now, this is actually very similar to what Apollo actually did. Apollo had a module waiting in the low lunar orbit while the rest of the crew went to the lunar surface to do the exploration. So in a sense, it is kind of a validation, right? It actually can replicate, although the numbers and everything are different, but it's replicating similar thought process we had back then, of course, when we didn't have all these methodologies. But what makes it even more interesting is, what if we have a repeating mission? So instead of doing this once, we have it. We need to do this 3 times, right? We need to send human to the moon 3 times and back. Then do we want to repeat this 3 times, or do we want to do something different? The optimizer says that let's do something different. So here the optimizer says let's take advantage of the lunar resource. We send ISRU, and the optimizer will size ISRU. Optimizer will size the spacecraft capacity so that it can carry ISRU. It can carry ISRU with it, and it also tells you how we take advantage of that ISRU, how much resource it generates at the second mission, and so that you can launch less and take advantage of this ISRU. There is some module waiting at low lunar orbit, basically serving as a proton depot, and so on. So as you can see, the first mission requires the largest launch mass. It's larger than the single mission case, but the third mission only requires a very small module and a smaller mass. And in this case, ISRU becomes effective if you have 3 missions or more. Yes?
Here are you minimizing the sum of the initial mass of each of the mission?
Yes, so here we are minimizing the sum of all the launch mass over the entire campaign.
So you're kind of assuming that the cost is linear in the initial mass, right? Because if the first mission is significantly heavier than the next 2 missions, it might, like, the cost might actually be even greater than the difference in the mass.
Yeah, so this here, yes, in this particular case, it's assuming all the basically there's no discount rate, right? But every year you get the same value per dollar. Of course, in reality, you can have a different metrics, and then the result will be different. So that depends on how you input into this model. The result will be different. Yes. Thank you. So this is, again, the purpose of this case is to demonstrate, right, that this tool works. And we have actually run a bunch of different cases. We have done a sponsored project with United Launch Alliance, which is a rocket company based in Colorado, and we for them, we actually use cost value. So not launch mass. We actually had a cost model and we did cost benefit analysis using this tool. So this is just for demonstration purpose. Okay, so this whole optimization, this is an approximate solution. So it's not the optimal solution. So this is a kind of this intermediate phase. But this approximate solution can be obtained within 5 minutes using Groovy, approximately 5 minutes using Groovy, which is nice. And so it can replace a lot of the manual design effort that has happened in the past, space mission design. Because in the past, when people look into these missions, people start to think about, what about this? What about this? But this can provide a objective assessment of different technologies. So from here, I want to talk a little bit an extension, another study we did as a follow-up to what I showed earlier, which is about how we can consider different propulsion systems in combination. So like I said earlier, the space mission design can consider different types of propulsion system. And one typical trade-off we consider is this high thrust trajectory and low thrust trajectory, or high thrust propulsion system, chemical propulsion system, or low thrust solar electric propulsion system. So chemical propulsion system is not very efficient, but it's impulsive, meaning it has a very high thrust. So you apply your velocity changes immediately, you're on the way to Mars. And low thrust instead, like I said earlier, it has a very small acceleration. So it becomes a control problem. So you need to continuously accelerate over a long time. And how much it takes and how much fuel you need will depend on what you carry. So again, you don't know how much you will cost until you know how heavy you are. So it's like you're trying to buy a plane ticket, but you don't know how much it will actually cost depending on what you eat the day before. Right? So you need to consider the entire mission design, including what you eat the day before and where you're going, instead of only look at where you're going. So that's basically the idea. So we need to actually consider the trajectory model. We can't just ignore the trajectory model as a pre-calculated model anymore. But we don't want to load the entire trajectory model in the optimization, because that will blow up the computation. Each trajectory evaluation can be very expensive. So what we did is we consider an approximation model using a Q law, which is a Lyapunov feedback control law. It's not optimal, but it provides a very good approximation for the orbits in the Earth vicinity. And then we leverage cislunar or space restricted three-body dynamics, particularly the invariant manifold around the equilibrium point in the cislunar space. And using this, we develop a method to quickly compute the orbit cost from the Earth orbit to, for example, the orbit in the cislunar space. And then, but even that is quite expensive if you want to plug that in or create a lookup table that can be a very massive lookup table. So we try to approximate it using a piecewise linear approximation. So actually, as you can see, the curve is mostly linear, or at least piecewise linear. And this is not actually by accident. There is actually physics-based reason behind it. Because of the way the trajectory design works, which I'm happy to discuss if you have time. But in either case, in this case, we can generate this piecewise linear approximation, and we plug that into the MILP. But that's okay if you're only interested in the fuel cost, but you are also interested in the time of flight. So like I said, the time of flight will really depend on what you're carrying. So you don't know the time steps before you run the optimization. So you can't pre-generate a time expanded network, say, oh, let's use this as your time expanded network. You have to generate your time expanded network on the fly. So we basically developed this event-driven network. It's basically a little bit constrained version of time expanded network. We don't assign the time steps at each event. So we don't know the time steps until we finish running everything. But at each event, you can have multiple things going on in parallel. But we have some specific mathematical condition that define an event. Basically, what that says intuitively is that each event has to be independent, right? You don't want to have an interaction happening between different actions within that event. For example, you don't want to say, we want the spacecraft coming here, spacecraft another spacecraft coming here, we exchange some commodity and go to the next one. Then that exchange commodity has to happen concurrently, right? So we need to know the time steps. So that needs to be the separation between the events. So there are some mathematical definition about how the events can be defined, but once you define that with the constraint I just talked about, we can have this event-based network and without time step assigned. The only constraint is that the total time has to be within whatever constraints you have. So that is kind of the approach we took, and this is the result. I will not get into the result here in detail, but the idea is that you can consider different trade-off between the mass and time. And this is, again, a typical trade-off when you consider the high thrust and low thrust. Again, high thrust is very inefficient in terms of mass, but it's very fast because it has high thrust, literally. Low thrust is very slow, but it's very efficient. But that is only for one trajectory. And here you are seeing this for the entire campaign, right? We are considering multiple missions, and each of these data points, we have this entire mission sequence. So we can consider this entire mission sequence and do a trade-off at this campaign level using this metrics of launch mass, immediately is a launch mass, and the flight time. So that's kind of the benefit of having this kind of approach. So again, compare with a traditional trajectory design, which focus on one single trajectory and doing the trade-off between time and the cost. Here we are doing that at campaign level, and that's possible because we can optimize the entire campaign in a very efficient way. So I've talked enough about exploration application. So from here, I want to briefly talk about the other two applications I showed earlier. One is about on-orbit servicing. So on-orbit servicing, like I said in the beginning, it's about repairing some satellite or refueling some satellite in orbit. DoD has been very interested in this. We had a multi-year project with DARPA to look into this particular problem. And so there, the problem we're looking into is how we can consider infrastructure, how we can design infrastructure system in geosynchronous orbit to provide a responsive service to the needs of satellite repair. And we don't know when the satellite needs repair. We can't predict exactly when satellite needs repair, and we don't know which satellite will fail next. So it's very similar as how we design a fire station on the ground, except that now we need to consider orbital dynamics. We need to consider the constraints. So it's like a queuing model. It's like spatial queuing model. We call it orbital queuing model. Actually, we didn't call it, but we can call it orbital queuing model because it considers orbital dynamics in it. And also we need to consider the inventory model as well, because that governs the launch. The difference between the space and the ground is that you have a very tight resource constraint in space, and the launch is very stochastic. And the storing some spare in orbit can be quite costly. So you need to consider the inventory model that governs the spare depot in orbit, and you need to consider the queuing model that governs the trajectory and the planning perspective. And so they are coupled models. So we developed a semi-analytic model to enable this calculation. It's basically an extension of MG1 and NQ, but with orbital mechanics and with the inventory model coupled with that. And so traditionally in the industry, I worked with the industry on this project, and they typically run expensive Monte Carlo simulation to evaluate a strategy. So it makes it very hard to do a large-scale optimization. But having the semi-analytic model, they can run optimization in a very efficient way. And for small satellite constellations, like I said, we are dealing with a scale that we have never dealt with in the past, hundreds or thousands of satellites. There are a lot of challenges associated with that, like how do we deploy all these satellites and how do we manage the debris? But one of them is about how we consider the spares to achieve certain reliability requirement. So in the past, we just have a constellation plane. We have one more satellite per plane. That was enough in terms of satisfying requirement of reliability. But when you consider this, large scale 100,000 satellite, that would not be enough. So the approach we took is to consider the multi-echelon inventory control model, where you have this, constellation plane as your retailer, and the ground is your supplier. And then we can design a set of parking orbit, which corresponds to the warehouse in orbit. And of course, the choice of this parking orbit becomes a very important design parameter. Now, all the lead time is stochastic. The launch schedule, of course, is stochastic. And the transit between this parking orbit and the constellation plane is stochastic if you want to pick the cheapest transfer, because the parking orbit is not necessarily in the same plane as your constellation plane. And in order to have a cheap, efficient in-plane maneuver, we need to wait until the opportunity comes. So here we take advantage of the natural orbital perturbation in low Earth orbit, which is caused by the fact that Earth is not a perfect sphere. So that actually will drift away the orbit. So we take advantage of that perturbation and create a stochastic lead time model that basically tells us how long we have to wait until the next parking plane that has available spares and matches with constellation plane in the same planar transfer, make the same planar transfer possible. So that's kind of the lead time model. I'm happy to discuss more, but here I just gave a very brief overview. Essentially, it's a multi-echelon inventory model, so it's all analytic, except that it is all analytic, and then we have to consider the natural perturbation in this lead time distribution. And by having that, we have shown that having this parking orbit, if we design it optimally, we can save the cost up to 40%. So that is another industry project we did. So this is my summary slide. So it is a very exciting field to space logistics, again, at the intersection of traditional aerospace engineering and logistics. The traditional aerospace engineering at the space mission design phase rely on manual design effort, but here we're introducing the mathematical analytics that that ISYE members will be very much familiar with. But we're trying to introduce that into the space domain and customize it for orbital mechanics and other unique space challenges. And what's particularly exciting is that it's responding to the timely needs. NASA is trying to have a big campaign, Artemis program. It just get started. And we also have commercial companies like SpaceX, and Northrop Grumman has its own on-orbit servicing vision, and NASA beyond international partners like European Space Agency. They had a space logistics workshop. I was invited. That was before pandemic, and I went to Netherlands, and they were very excited about all this particular vision for future space mission design. So this growing complexity in space missions really is driving a lot of emerging needs in the space logistics field, which is why I think this is very exciting. So lastly, I want to acknowledge my students. Some of them are here, and many others, including the current members and also past members. And we have a website at the bottom. If you have any questions, please feel free to email me at any time. So that is all from me. Yes. Yes.
So I'm wondering, I think in many of your models, you consider some kind of deterministic planning. So I wonder if you also consider, say, risk, or know that, of course, in our everyday supply chain, right? So we have supply chain disruptions and supply chain bottlenecks. I wonder if you consider those in your space model too.
Yes, that's a very excellent question. The question about uncertainties. So I actually have backup slides on that. So there are many studies we have done in considering uncertainties, particularly considering how we react to different uncertainties. And one of the uncertainties that we have considered is actually there are several types. One is launch delay, which is not the one that I'm showing here, but So if we have launch day like we just had, how do we react to that? Essentially, the idea is to have a little bit more safety stock in space, but then how do we optimize that, and how do we optimize the transportation and so on? So that is doable, but that is relatively simple because we can define a parametric model about how we react to these uncertainties, and we can optimize these parameters. And this one is a little bit different. It's about uncertainties in the new technologies like ISRU. So ISRU is, although we have more and more technology development in this area, we have the only example of ISRU that has been demonstrated in space is using Mars oxygen to generate use Mars atmosphere to generate oxygen. But again, that's at a very small scale. So there are a lot of uncertainties in the parameters we use in ISRU, for example. So, so this is basically a stochastic optimization problem, but since the problem becomes very large, so it's not necessarily efficient to put everything into a stochastic optimization problem. So what we did is we consider reinforcement learning, but we can't just use reinforcement learning to do everything because we have a lot of decision variables. The action space will be huge. So we essentially got inspiration from this hierarchical reinforcement learning, and say reinforcement learning, we use reinforcement learning to provide high-level guidance of each missions. And then each mission is optimized using MILP. And then we have an outer agent that optimizes spacecraft. And so it becomes a hierarchical structure, and but because of the capability of reinforcement learning to consider different stochastic scenarios, this can optimize optimize the entire mission planning under uncertainties, and while taking advantage of the fact that the MILP can actually run each mission in a very quick way. So that's kind of one way we have considered, but I'm open to other ideas if there are other ways to tackle this uncertainty. That is definitely an ongoing research topic. Thank you for the great question. Yes.
Yeah, hopefully this isn't too philosophical, but what do you see as the like the biggest barrier to large scale, like campaign level human space exploration? Would it be technical or economic, like closing the business case of this, or even like political?
Yeah. So I mean, all of them essentially, but
I guess where would we get the most bang for the buck?
yeah. So of course the cost is a big issue, especially we don't expect a lot of benefit through space exploration in reality. I mean, a lot of the motivation behind space exploration is more driven by science missions or national pride and so on. So it's less about profit. So the cost is definitely a significant driver. So there are a lot of studies, including our group, but many other groups have been working on affordable space mission, right? How do we make sure that the cost per year is within the limit that NASA actually has, that may delay some of the missions. So what we can delay, what we cannot, and what is the trade-off there, and so on. So the cost is one of them, and politics is one of them. So if you see the U.S. space program, it changes basically every 4 years, every 8 years, right? Every new president basically have their own vision. But what's nice recently is that Biden administration basically continued what Trump administration was proposing. So at least in the current political environment, I think it's favorable for space for space exploration perspective. But in general, that can be one of the barrier, because of course budget is of course driven by the politics, and many of them is unpredictable. So actually, regarding uncertainties, one of the big uncertainties is that, and how do we consider the continuous? How do you ensure that we have a continuous investment in this field? And what if some significant disruption in investment happens? How we can deal with that? So that is of course an important question, but it's also very hard to deal with, because when you say, okay, we can consider worst case, right? Robust optimization, we consider worst case, but what is a worst case, right? Worst case is nothing happens, right? So does that even make sense as a consideration? And if you want to use chance of constraint optimization, then what is the probability distribution you're talking about, right? For a lot of these uncertainties, we don't really have a quantification. So that's where the mission design becomes a little bit challenging. But coming back to the question, what would be the road barrier? I think this cost and politics definitely will be a very significant barrier. But I think again, under the current political environment, I think it's relatively positive in my opinion. Yeah, thank you.